So our speaker today is Rufus Willett, and his title you can see is there is Conditional Representation Stability and K-theory. Please, Rufus, go ahead.
Thank you very much, Willie. Thank you very much for the invitation to be here. Thank you particularly for the repeated invitation after I did not make my original talk time 2 weeks ago. And thank you to those members of the audience who were here 2 weeks ago when I wasn't. So that's nice to see everyone and be here. It is 3 in the morning in Hawaii, so please ask questions, but treat me gently when I answer them slowly. I will try and do my best to be awake and on top of things. So this is a talk about conditional representation stability, whatever that is. It's been a subject of quite some interest in group theory, particularly over the last 10 years or so, insofar as it connects to various approximation properties of groups. And the and K-theory bit is because I want to try and make the point that techniques from K-theory, 2 aspects of K-theory, particularly the sort of parts of K-theory that go into the classification of C-star algebras, but also the bound-Kohn conjecture, are relevant to this, at least in some parts of the theory of representation stability. So I'll start with just some general background and motivating results. All of that is relatively old and certainly not due to me. Starts little over 40 years ago in the early 80s, and then going through results about 20 years ago, although there's a few that are a bit more recent, but this is all stuff that's pretty old at this point. Then I'll talk about controlled K-homology, which is something that Guliang Yu and I introduced for a somewhat different purpose. So I should point out that this bit is linked with Guliang Yu. And that is closely connected to a special class of approximate representations called ECP quasi-representations, whatever those are. I'll get to that later. And then I'll talk about the main results and at least sketch the ideas that go into the proof. It's a fairly long and technical proof, but a fairly, at least long proof. I just want to give at least the idea. I won't state it in full generality, but I'll at least state a representative result. Okay, so this bit is background. So the motivating vague question, which you can ask in many contexts, and it's sort of in the spirit of numerical analysis in some sense, it's relevant if you're using computers to find approximate solutions. So if you have something that approximately looks like a solution to a set of equations, maybe you've got a collection of polynomials, for example, then is that thing which is very close to satisfying the equations, is it close to an actual solution of the equations? And the answer may be yes, maybe no, depends on what you mean, what close means, what sort of equations you're looking at. So this talk for representations will come from group theory. I'll come from finite presentations of groups. So the context will be a finitely presented group. That means I have a finite set S of generators and a finite set R of relations, and the group will be the free group on the set of generators quotiented out by the normal subgroup generated by the relations. Key examples for that, at least to begin with, and these exemplify quite different aspects of the subject of representation stability. So the first basic and most important example is just a free abelian group of rank 2. So generated by 2 symbols A and B. The set of relations, the things that you're setting to be trivial, is the just given by the commutator, a multiplicative commutator of those 2 elements. It will be important, but sort of in the background, that this group is the fundamental group of the 2 torus. There's a picture of the 2 torus, so it's generated. It's the standard picture here where you identify these two sides and these two sides, and this word that you're sending to be trivial is what you get by following that around the outside. Similarly, this is a semi-direct product of the acting on itself by the non-trivial automorphism, so just flipping things. And that is, again, group generated by two generators, almost the same relation, but it's this time there's no inverse on the last B. So it says that if you conjugate B by A, you get B inverse. And that one is the fundamental group of the Klein-Boffel, and again, given by the standard picture. The presentation too complex, or if you like, in both cases, the two torus is the classifying space of this group. Again, that will be relevant later. And the Klein-Boffel is the classifying space of this group because they have contractible universal cover in both cases. So those two examples will come up a fair amount. Then slightly silly definition, but it's equivalent to the definitions that you know, of course. So because of what will happen next, I will define a representation of such a group. So this is UN is the finite dimensional unitary group and by n unitary matrices. And representation will just mean that you pick somewhere to send the generators that will canonically extend to a representation of the free group just by following words, and it should send all words in the set of relations to the identity. So for example, a representation of C squared just means Z squared just means you pick two unitaries and you ensure that they can send those relations to 0. So that's the reason for stating it in that slightly weird way is then you can find an epsilon quasi-representation to be a map from the set of generators again to a finite dimensional unitary group, so that when you extend pi to the free group, it doesn't necessarily kill all those representations, but it sends them to something which is close to the identity up to the given tolerance epsilon. Super important for today. All norms are operator norms. You can define epsilon quasi-representations in several different contexts. You could put other norms here depending on taste and what you're interested in. But for me today, they will always be the operator norms. People are very interested in other norms you can put on these. For example, you can consider the Hilbert-Schmidt norm here, which is the norm you get by squaring all the entries, adding them up and taking the square root and possibly normalizing, possibly not, depending on taste, but always the operator norm today. And then there's a standard of closeness. So this is an approximate representation. Sorry, it shouldn't be there. This is the standard of closeness of such things. And it just means that you've got two of these things, so there are two choices of S generators, and they are close if they're just close on the generators. So it's a sort of point-wise closeness condition. And then we have the general motivating vague question from the start, which is if we have something that approximately looks like a solution to our set of equations, is it close to an actual solution? Okay, in this context, how we're going to make that precise is if we have our group and any epsilon is there a delta such that any epsilon quasi-representation is delta close to an honest representation. Now, there's something I've sort of swept under the rug here that's just to keep this implicit, but there's an N here. And this is for any epsilon quasi-representation. And it's very important that the delta does not depend on the N. So you want to do this uniformly independently of the size of the matrices. If you did allow delta to depend on N, then the answer is yes, for fairly few reasons. Surprise, I guess. Okay. So that's the formal definition, and that's the definition of stability. So if you have your finely represented group gamma, it is stable if for any epsilon there is a delta. So any epsilon quasi-representation is delta close to an actual representation. Again, the delta does not depend on the on the N. And maybe just write down explicitly this does not depend on the presentation. So to finally present a group and to define epsilon quasi-representation and delta close, fix the presentation. But whether or not the group is stable does not depend on the choice of finite presentation. Of course, the specific delta that you get dependent on the epsilon will depend on the finite presentation, but whether or not the thing is stable. Okay, so two theorems quite far separated in time, but from the early 80s, first theorems on this in fairly different contexts. So David Kazhdan working explicitly in the context of group theory, essentially proved this, and then Voiculescu working in a more operator theoretic context motivated by a question of Paul Halmos from the 60s, proved that completely different proofs, and I think they were completely unaware of each other's work, proved that the group G squared is not stable. So the fundamental group of the torus is not a stable group. On the other hand, Suter, Søren, Eilers, Terry, Loring, and Gert Pedersen, so about 15 years later in the late 90s, showed that the fundamental group of the Klein bottle is stable. So these have two fairly different behaviors, even though these two groups are pretty close, right? So the free abelian group of rank 2 is an index 2 subgroup, and the fundamental group of the Klein bottle, those two groups look pretty similar. But for this one, there are epsilon quasi-representations which you cannot approximate by actual representations. For this one, if you have a suitably good epsilon quasi-representation, it will automatically be close to an honest representation.
So the moral is that I mean that stability is not, it's not that the nicest groups on Earth, but the more commutative ones and nicest are the stable ones, and the bad ones are the non-stable. This example shows that that's not the case, right?
Yeah. So I mean, this group is something we think probably is being simpler than this one, but that's not the case. What will happen eventually is it will be about group homology, and it won't really be about group homology. It will be about K-theory. And the point is that this one has more complicated K-theory than this one due to the fact that essentially this one is a fundamental group of something where there is a non-trivial Bott bundle. It's a fundamental group of something orientable. This one, that doesn't happen. This one basically has trivial even dimensional homology, and that's all that turns out to be relevant, but it's more complicated than that. Get to that later. Okay, anything else about those examples? Yeah. I should maybe mention that free groups, not free abelian groups, free groups are trivially stable because it's vacuous. If there are no relations, then the whole thing is vacuous. So those are the nicest groups from this point of view of this theory. Finite groups are also stable, but for, again, silly reasons. Okay, so I'm getting sort of more towards the spirit of K-theory. This is a fairly ad hoc definition for the purpose of this talk, but not unreasonable. An additive invariant of quasi-representations of your group is going to be a map from the set of epsilon quasi-representations. So an epsilon quasi-representation is just a, choice of S unitaries. So it's a map from the set S to the unitary group, the nth unitary group. So I'm thinking of the epsilon quasi-representations as sitting inside this disjoint union. G is an abelian group. It will probably be Z, but there's no reason it has to be. I think for all my examples today, it will be Z. It should vanish on actual representations. It should be uniformly continuous, where the metric on this is, say, any metric that restricts the one coming from the operator norm on each unitary group separately, or each product of unitary groups, sorry, separately, and say that gives the different UNs, makes them distance 3 apart from each other, or something like that, whatever, some finite distance apart from each other. It should vanishing representations, and it should be additive. Now, one of the important things going on here under the hood is that because we're using the operator norm, if you take a direct sum of 2 different representations, if you have 2 epsilon quasi-representations, it's still an epsilon quasi-representation because the norm of a direct sum of matrices is the supremum of the norms of the individual matrices. Now, that wouldn't be true if we were using different matrix norms, so that's one of the places where it's important we're using different, that we're using the operator norm and not, say, the Hilbert-Schmidt norm or trace norm or whatever. For some reason, I wrote these the other way around on the right-hand side, not important. Take block sums to sums. Okay, so the basic example of such an additive invariant. So again, for a abelian group onto generators, and this is how Kazhdan was thinking about this in the early 80s. It was rediscovered later in the early 90s by Rufus. Just completely independently. I think Excel was working on understanding Voiculescu's result more conceptually. So what you do is you take your quasi-representation, you look at this commutator. This is something which is close to the identity because it's a quasi-representation, so this commutator will be close to the identity. So this path is a straight line between the identity and something which is within distance 1 of the identity. Therefore, the entire path stays within distance 1 of the identity. So this thing is invertible. Take the determinant, you get a non-zero complex number because you're looking at a path of invertible matrices. Moreover, when t is 0, it starts at the identity, and when t is 1, you get the determinant of this commutator, which is also 1 because it's the determinant of the commutator, right? So this thing is a path which starts and ends at 1 in the complex plane and avoids 0. Therefore, it has a winding number. Okay. So this is something which belongs to the integer valued invariant of quasi-representations, and check that it's additive in the sense of because the product of paths field determinants take block sums to 5. Yeah. And a product of paths for winding numbers, sum of the winding numbers. So this is now, we sort of go back to the theorem. So Kazhdan, how Kazhdan did this. Voiculescu did not do it this way exactly, but if you reinterpret Voiculescu's result in the spirit of Rufus and Terry Loring from the early 90s, then the theorem is that this thing is not stable because for any epsilon, there is an epsilon quasi-representation with this winding number equal to 1. Because this winding number invariant is uniformly continuous, that means that you therefore cannot be close to an actual representation, because if you were close to an actual representation, well, if you're close to an actual representation, then this whole path here is close to a trivial path, so it has trivial winding number, and it will go away.
May I, sorry to interrupt you, may I ask you this? A very stupid question. So, this one is an identity matrix, right?
Yes, yes.
Okay, and T is T times the identity matrix.
T is T times the identity matrix, yes.
So if T are, okay, and the pi's are, yeah. So, okay, this is small, but it's still an invertible matrix. The thing. Next to, okay, so when T is 1, you get that invertible matrix, and when T is 0, you get the identity.
Yeah. Yeah, exactly. So this is it's a straight line path between the identity and the thing, which doesn't look like it has a non-trivial winding number, but then this is a degree n polynomial, so it can take that straight line path to something non-trivial. And there are examples. And the examples are the simplest thing you would try. You send A to the matrix with the roots of unity down the diagonal, and you send B to the shift matrix, which commutes those things by cyclically shifting them. And those two things will have small commutator. The winding number will in fact be 1 though when you do that, as long as you take them suitably large. So the nicest possible thing works, which is the example that both Voiculescu and Kazhdan found. Okay. Any more questions about that winding invariance? One thing I'll note, by the way, for this to be well defined, why doesn't this work for the Klein-Bottle group? It doesn't work because this isn't a commutator. Therefore, its determinant is not 1. So if you did this with a Klein-Bottle group, you would get a path. But although it starts at 1 when t is 0, it is not 1 necessarily when t is 1. So you don't get a path that starts and ends at 1. There is no well-defined winding number. So it's crucial that this thing is a commutator. Okay. In order for that invariant to be defined. Next definition, so I'm going to go through some slight variations of stability now. A finitely presented group is stable, conditional on vanishing of a certain number of additive invariants. If for any epsilon there's a delta, so that as long as you have a quasi-representation where these invariants will vanish, then it's close to a representation. So those invariants are the only obstructions being close to an actual representation. Very nice theorem independently due to Dong-Lin from 98, Eilers-Shulman-Sørensen from 99, so the same team of authors who did the Klein-Bottle group case. So although d squared is not stable, this invariant W is the only invariant that sees that. If you have a quasi-representation where this winding number invariance is trivial, then you can perturb the pair of matrices to an actually commuting pair of matrices. This is the only thing that tells you you can't do that. That's math. Okay. And that's the sort of theorem that I'll be aiming to generalize. Now I need one more variation of the definition of stability before we get there. Yeah, and right, I said this already, but let's make it explicit. In some sense, the reason for the stability of the fundamental group of the Klein-Bottle, but only the conditional stability of this thing, is that the second homology of the Klein-Bottle is 0. Sorry, non-orientable, sorry. The second homology of the two torus is Z, orientable, two manifold. But okay, it's not, I will claim that it's not really about homology, it's really about K-theory. And it's the Bott bundle on the two torus and the absence of such a thing on the Klein-Bottle is what's relevant here. We'll see hopefully a bit more of that as we go through. Last definition in the background bits, finitely presented group is weakly stable. It should probably be called stably stable or something like that, but that's terrible terminology, so won't. But what it means is that you can find honest representations so that when you take your quasi-representation, you block sum it with your honest representation, that is close to the other honest representation. So maybe you can't get your thing itself close to an honest representation, but if you take its block sum with an honest representation, then you get it close. Now, for the sort of thing the group theorists are interested in, this is still good enough for the sort of applications they want, which is obstructing various approximation properties. I'll go into that. And you can do this conditionally as well. It's the same thing, but you assume that a load of additive invariants vanish. So two theorems along these lines. This one is again essentially due to Gong and Lin, same paper as before. So if we go up a dimension, if we go to the Fourier-Abelian group of rank 3, okay, this time we can define 3 separate winding number invariants, one for each pair of variables, which picks the generators. Then we get 3 separate ones, which can all be non-zero independently of each other. This thing is weakly stable, conditional on vanishing of those. If all three of those vanish, that will tell you that any quasi-representation, good quasi-represension, would be close to an actual representation. However, it's not stable. You genuinely need to add this auxiliary thing, annoyingly, but it just seems to be a necessary feature of things as soon as you get above dimension 2. Similarly, this is much more recent, but essentially due to Marius Dadarlat in 2021, which is that there is a three-dimensional flat manifold. So again, it's a fundamental group of a three-dimensional manifold. It has this thing, excuse me, as a finite index subgroup. Fundamental group, sorry, has these cubes as a finite index subgroup, weakly stable, but it's not stable. Again, and again, the special thing about this particular flat manifold is that its two homology is torsion. These things here are corresponding to the two homology of 3 torus. It's a rank 3 abelian group, rank 3 abelian group. Generators correspond to the generators. But for this manifold, excuse me, the second homology is torsion, as is the reduced K homology. And that's relevant to what's going on. Okay, so that's all the background. That's all the definitions we need, and I'll start moving on to the tools needed in the proof. So this is the second part on controlled K homology and UCP quasi-representation. So completely changing tack slightly. We'll take a separable unital C-star algebra and represent it on a Hilbert space. Okay, I'm assuming that such a thing exists. So assuming it has a direct sum of finite dimensional representations, which is faithful, and then infinite multiplicity just means I take that faithful representation and I add it to itself infinitely many times, counted infinitely many times. So it's represented on a separable Hilbert space via a direct sum of finite dimensional representations, where each of those finite dimensional representations is repeated many times. So okay. Assume that such a thing exists. It may or may not in general. Then we will do the following thing. So for an epsilon greater than 0 and x finite, and you should think, by the way, A is a group C-star algebra and X is a finite subset of the group. We will consider the set of projections in 2x2 matrices over B of H, which are compact perturbations of this sort of trivial matrix. Going to play the role of the identity in this setting. They're projections. And then the crucial condition is that they approximately commute with all elements of the given finite set. Okay?
Sorry, yeah. One I bother you again. So the condition on the separable unit and C-star algebra, in the case when the algebra is the C-star algebra of a group, does it correspond with some property of the group, like being sophic or whatever?
Yeah, it's related to that. So if A is C-star gamma, such exists if and only if gamma is, well, it's called RFD, which stands for residually finite dimensional. And what it means is finite dimensional representations are dense in its unitary dual, felt topology on its unitary dual thing. So in other words, it says that this thing has a faithful representation, which is direct from finite dimensional things, and that's a property that some groups will have and some won't. If it's a finitely generated group, this implies that the group is residually finite by Marchev's theorem, because it implies that it's residually linear, and finitely generated linear things are residually finite. So it's stronger, but it's stronger than residually finite in general. There are residually finite groups like SL3Z, for example, is residually finite, but it does not have this property. So it's an assumption, definitely an assumption. Quite a strong property. For an amenable group, it is equivalent to residual finiteness, though, because you can just take the direct sum of things that factor through finite quotients, and that will be faithful on this for an amenable group. Okay. So we take these projections, then we define a controlled K-homology group just by taking the path components. Okay, it's not immediately obvious it's a group, but it is. The identity is the class of this matrix, and it's a group because I forced this to be infinite multiplicity. Therefore, there are a pair of isometries satisfying the Kuntz O2 relations in the commutants, and I can use those to define Kuntz sum on these things, and that makes it a group in a completely canonical way. It doesn't depend on any choices involved. Moreover, if epsilon gets smaller and x gets bigger, then it is harder to commute with the bigger set up to the smaller tolerance. And that means there are forgetful maps between these p epsilon of x's, which make the collection of all these groups into an inverse system, ordered in such a way that as x gets bigger and epsilon gets smaller, and we'll define this group KL0 of A to be the inverse limit of these things. So that's another abelian group. It's canonically a topological group. So you take the inverse limit in the category of topological abelian groups where each of these things is given a discrete topology. So that's a nice topological abelian group. It's called KL because Mikhail Rodin called it that in a different context in the 90s. I don't know why BL is there, I should ask him. It's what it is. Okay, and that definition is due to Yang and myself. Now, how does that connect to the sort of representations we're interested in? Let's say we've got a finitely presented group, and we've got the full group Caesar algebra. So take the group algebra and complete it in the norm, which is the norm that gets into the cream of all representations, represented in the way above. And again, it's an assumption that such a representation exists. Then I need one more class of quasi-representations. So UCP epsilon quasi-representation is a map of form. Okay, so again, member generators to bounded operators. And what we're going to do is take the unitaries in this representation, which are just the canonical unitaries, and we will compress them by a finite rank projection, which approximately commutes with them all. Okay? And that will basically be a quasi-representation in the sense above, in the sense that we had earlier, except that's a slight lie because this won't be unitary, but if you drop that condition and allow yourself things that are only invertible, then it would be okay. So this is, it's almost multiplicative by this condition. And if you have one of these things, so if you've got a UCP epsilon quasi-representation with associated projection P, then you get a class just by taking a class of this matrix in this controlled K-homology group. So the difference between 1 here and P with just 1, 0, 0, 0 is compact because P is finite rank. This thing will approximately commute with all the operators in S because we defined it too. So this is a well-defined class in this controlled K-homology group.
So one thing in the definition. So in the definition of UCP epsilon quasi-representation, so the compressing is meant to imitate, say, the UNs that you had before because these are finite.
Finite rank, yeah, exactly. Yeah,
yeah,
this is living in a finite dimensional matrix algebra.
Yeah, but you could have infinitely many P's with different, all equivalent to all of rank n, say, in different places, which was not allowed in the original thing, was it? Or did you? So I mean, I don't know if I misunderstood, but I thought of one representation in each UN for each N. And now we are having 1,000 representations all with the same N for many, I mean, for 1,000 P's, all of rank N that are orthogonal.
Oh, they will be in different places. Yeah. Yes, they will be in different places. I'm not fixing where as a subset of this subspace they are. If they're in different places for trivial reasons, then there will be homotopic, so there will be the same class in this group. But that could happen. There'll be homotopic through things in the commutant, but if that happens for trivial reasons, so where they are is maybe not important as far as the class in this group goes. End up happening. Does that answer the question? I have about 10 minutes left, is that right? Yeah, okay, cool. So I'll sketch for proof, but I'll do it fast because I just want to state the main ideas, and it's kind of long. Oh yeah, one extra thing I need. C-star algebra satisfies the universal coefficient theorem of Rosenberg and Schockett from, again, the 80s. If it is, I'm just going to do this in a really ad hoc way. If it's isomorphic in the KK category to commutative C-star algebra, you don't know what that means, doesn't matter. Nice assumption. And then theorem combining work of several different people. So Marius and Terry from 96, Marius from 2005, myself and Guliang from 2024-ish, which means the paper was written about 5 years ago. And hopefully it will actually appear this year, but hopefully if not soon. So separable unital UCT C-star algebra. Again, if it's a group C-star algebra, the UCT is known in certain situations. Then there is a homeomorphic isomorphism between this KL group, this inverse limit of control K homology groups with its inverse limit topology, and the group of homomorphisms, morally the group of homomorphisms from the K-theory of A to the K-theory of the complex numbers, except that's not quite enough. So what you do is you take the K-theory of your thing, and you take also all the K-theory with finite coefficients, and you have coefficient change operations, so-called box-line operations, act on those, and you take the homomorphisms between those groups, which are consistent with those operations. Morally speaking, this is just homomorphisms from K0 to K0 of A to K0 of C, but that's not actually what it is, and you do need these things with finite coefficients, unfortunately. Okay, so that is, yeah, and here the K-theory with finite coefficients, following Schockett and Schockett when they originally introduced these things, and really, I guess, going back to work of Matthias Singer in the 70s and probably earlier. Oh yeah, there is an earlier definition in algebraic topology due to Dold, I think. We'll take the K0 group of A tensor, the corresponding Kunz algebra, the actual definition in this case. Okay, so that's what the universal coefficient theorem will say in this context. Yeah, and it's a version combining work of a few different. All right. So I won't state the main theorem in full generality. I'll say a little bit more about that at the end, but the point of most of what I'm saying is to do things for non-amenable groups. All the previous work was for amenable groups, and I want to do things in the non-amenable setting. About the simplest case that we can deal with is something like this. So take a free group on N generators, act on it by a cyclic group, and take the corresponding semi-direct product. Now, the automorphism that you use to define that will induce a map from the first homology to the first homology of the free group. So that's just a map from Rn to Rn. It may or may not have one as an eigenvalue. If it does, then we'll let R be the rank of that. That rank is exactly the rank of the second homology group of this semi-direct product. And for each such class in the second homology, you can build a winding number invariant. And this group will be weakly stable conditional on vanishing of those winding number invariants. Okay, so let's very quickly go through the proof of this and say a little bit more about what it is in more generality. Step one is approximate by UCP quasi-representation. So you start with an arbitrary quasi-representation. You show that you can approximate it by a UCP quasi-representation. And that uses ideas of Voiculescu and Kazhdan. So the key idea is to use Kazhdan's local lifting property. For this particular group, the fact that it has the local lifting property, whatever that is from technical C-star algebra, is due to our students Booth, Siegfried, Hoff, and myself. And we'll show that that shows that any quasi-representation pi can be approximated by UCP quasi-representation. That's almost equivalent to the use, well, it's equivalent to a special case of the local lifting property. So a general quasi-representation by the construction earlier defines a class in some controlled K-homology group. Okay. What we're going to do is get rid of that class. That's the theorem. Step two, we prove a so-called stable uniqueness theorem in the sense of Dadarlat, Eilers, and Lin. This is working C-star algebra classification theory from the around 2000, so around 25 years ago. And the group C-star algebra of this group satisfies the UCT by Higson and Kasparov's proof of the Bampon conjecture. So we show that if this is the topological isomorphism coming from the UCT, this pi gives something which is at least partially defined over here, and therefore it corresponds to a partially defined class over here, and show that if this thing agrees with the class of a representation tau on a suitably large set, then you can find an actual representation so that the block sum of your quasi-representation with an actual representation is close to being unitary conjugate to this representation. Stated like this, this is the stable uniqueness theorem of Dadarlat, Eilers, and Lin if A were an exact C-star algebra, in particular if it were nuclear. It's not nuclear, and it's not even exact because this is not an amenable group. So this is a very bad C-star algebra. The work from 25 years ago doesn't apply. So you have to do something different. And okay, the controlled K-homology theory that Guliang and I introduced is a good language to do that different thing that you need to do. So step two is to reprove the stable uniqueness theorem in such a way that it works for non-exact C-star algebras. Okay. Third step is where the geometry comes in. So step three, compare with classes of honest representation. So we've got this partially defined class in some controlled K-homology group, and we need to, or in one of these Hom groups, and we need to compute the class tau of an honest representation in here, and we need to show that the class of that in this Hom group can be found to match this class pi if and only if all these winding number invariants vanish. At that point, the stable uniqueness theorem will say, okay, these are the same class in this Hom group, therefore we can get them to be approximately the same as each other up to unitary conjugation. Okay. Right, the problem with that is if we didn't need K-theory with finite coefficients, then we'd be fine. This would just on the nose be all these winding number invariants vanish because they're defined to have that property. Problem is that we do need K-theory with finite coefficients. So K-theory with finite coefficients splits unnaturally as a direct sum of the co-n torsion in K0 with the n torsion in K1. The hard bit is understanding what happens on the K1 part. So it doesn't look like you should need K1, but you do. And that you can compute using the relative eta invariants, so something from index theory defined by Atiyah Singer in the mid-70s. And this map on the torsion part of K1 as a map to the K0 group of C with finite coefficients. That's computed by the Atiyah Singer relative eta invariants, whatever those are. Some, again, index theoretic thing, which is defined geometrically. And the Bamcon conjecture lets you relate those two things to each other. It's important this splitting is not natural because the K1 group of complex numbers is trivial. So if it was natural, then the map here would necessarily be trivial. It's not. And the fact that these things cannot vanish, tells you that it's not natural. Okay. All right. So just to summarize, main theorem again. So just to very quickly state the give a slight idea of what the theorem says in more generality. There are similar results for other very nice classes of non-amenable groups. You throw enough machinery at it. Fundamental groups of surfaces is what I was actually motivated by. So the original case of torus and the Klein bottle, I wanted to generalize it to higher genus surfaces. And it more or less works in that case too. It works for Lamslot solitary groups, whatever those are. It works for fundamental groups of pretty much all prime free manifolds, whatever that is. And in all cases, the winding number invariance corresponds to the second homology of the group. The only caveat is that our friends in hard analysis have not proved the LLP for these classes of groups yet. I conjecture that they will prove it because it would be very upsetting if it wasn't true. So hopefully that will happen at some point. Once that happens, you would get the analog of this theorem for these classes of groups as well, and everything would work nicely. Okay, so out of time, and we'll stop there.
Okay, thank you very much, and thank you for putting up with all my interruptions. So, what's the meaning of the last sentence? What does it mean that the result holds for UCP quasi-representations?
Yeah, so it means that this weak stability means that for any epsilon quasi-representation, for any epsilon there is a delta, so that if all these winding number vanishes, blah, blah, blah. And it just
you need to add the UCP.
Yeah, you need to start with the UCP quasi-representation. So the first step was take an arbitrary quasi-representation, use the LLP to approximate it by a UCP quasi-representation. That step doesn't work. However, if you just start with a UCP quasi-representation, the rest goes through. So the other assumptions that are needed, which are things like the Bamcon conjecture is true in a strong enough form to give you the universal coefficient theorem, and you also need that the Bamcon conjecture is an isomorphism for the maximal group C star algebra that is needed to compute these relative eta invariants. Those things are all known to hold for these classes of groups. Also, the RFD property that the finite dimensional unitary representations are dense in the unitary dual, those are also all true for these classes of groups. So you need all that, but the LLP has not been proved yet due to, I don't know, due to an oversight by our friends in hard analysis. Sorry, silly, but
so
they didn't get around to doing that yet.
Are there questions from the audience? Let me see the chat. Nothing there. For the young people and the old ignorance, such as myself, what's the ring of Box-Thing operations? I've heard the word
okay.
7,000 times, but I never.
Yeah, sure. Sorry, I did all that bit fast, so just to give a sense. But yeah, let's say a bit more about
it's in the home, yeah.
Yeah, this thing here. So there's a few ways. I mean, this is not my favorite. Where was it? Not my favorite way of defining this, but I did it this way because people do it this way. Here it is. So you're looking at these things. It's the ring of coordinate change operations, essentially. So one way of defining it, which is the kind of cheap way of defining it, is you can take let's write it like this. So you can take the KK operations, takes the direct sum of all the ONs, and same thing. And then you can take, you don't want that, you want the subring of it, which is sort of finitely supported. So take the, going to call this O1 for simplicity. So you would take the direct sum from NN is 1 to infinity of KK OM as it sits inside here, where again, the complex numbers are being called O1 for simplicity. So that thing acts on all these things. It acts sort of on this direct sum of sort of finitely supported matrices, which change coefficients between the different bits. So that's one way of defining it. You can define it in terms of generators and relations in a reasonably nice way. It's generated by natural, all the various KK elements by Kirchberg-Phillips classification, if you like that, are induced by more or less honest star homomorphisms between the different Kuntz algebras, and you can do it that way. Classically, it's you don't use Kuntz algebras, you use more spaces, so something commutative. I use Kuntz algebras because, for technical reasons, I need a unital model. But,
okay. By the way,
yeah,
O1 should be the continuous functions on S1.
Yes, I know.
Yeah,
sorry, that's partly why I was apologizing. Terrible notation. Yeah.
So the complex number should be O0, but anyway.
Yeah, sorry, that would have been better. Yeah. I've done it even worse before. Because this is sort of off by, I don't really need n equals 2 because that one has trivial K-theory, because these are I previously defined O2 to be the complex numbers, which is even more upsetting to people. So,
yeah. Well, I'm honored that you didn't do the worst of you in this stuff.
Yeah, right.
Okay. So if there aren't any more questions from the public, I will stop the recording here.